Today, in Digital Labs, we're going to be looking at lab number 10, counters. And you can see we're going to need our breadboard, wire strippers, and wire. We're going to be using a 7408 AND gate, a 7414 Schmidt inverter, the 74112 dual JK flip-flop. And remember, the book uses a 7476. And the new IC is going to be the 74192, which is a BCD, or binary coded decimal counter IC. And we're going to be using the 74393, which is a CMOS counter IC. We need our 470 microfarad capacitor. We need 8 LEDs. We need resistors to go with them, and they're 330 ohms. Even though the book uses 150 ohms, we want ours to last a little bit longer. And we need a 2K ohm resistor. As always, when I introduce a new part like the 74192, I give you the pinouts for it. And the 74393, I give you the pinouts for those. But for the other ICs, I expect you to reference your previous labs. So our textbook is Sham's Outlines, Digital Principles, 3rd edition. We're going to be looking at Chapter 1, and we want to reference 1-2 and 1-3. And we're going to be looking at Chapter 10, so that's 10-1 all the way up to 10-6. When you've completed the lab, you should be able to answer the solved problems in 10.1 all the way up to 10.41. So Chapter 1 is numbers used in digital electronics, and Section 1-2 is all about binary numbers. And Figure 1-1 is all about counting in binary and decimal numbers, so please make sure you can count 0 through 19. And Section 1-3 is all about hexadecimal numbers, so Figure 1-7 shows you counting in decimal, binary, and hexadecimal numbering systems. Chapter 10 in your textbook is all about counters, and Figure 10-2 is a logic diagram for a 4-bit mod 16 ripple counter, and we're going to be building these today. Figure 10-12 talks about the 192 Synchronous BCD Up-Down counter IC that we're going to be using. And you can see around Figure 10-18, they talk about the CMOS dual 4-bit binary counter IC, the 74393, that we're also going to be using today. So lab schematic, Part A, Ripple Asynchronous Up Counter. You can see we're going to be using 4 JK flip-flops. Remember that the 74112 contains 2 flip-flops in each IC. So this represents 2 ICs. I always seem to get a lot of questions about U3 1 Hertz here. It says in the procedure here, use the circuit of Lab 9B to generate the approximate 1 Hertz input signal. Doesn't need to be exactly 1 Hertz, just close. Tells you to fill in the pin numbers above, construct and test the circuit, then complete the count sequence table on the right using 1s and 0s. And Figure 10-1 contains the correct answer. So this is the circuit from lab number 9, part B. And you can see we're going to use a 74LS14. And we've got a capacitor and a resistor that's being charged from the output and discharged from the output. So this is my 74LS14, and you can see I've hooked up the power, the ground. So looking down from the top here, you can see this is my 74LS14, and I'm showing it to you at this angle so that you can see the little resistor here. That's my 2K ohm resistor going between pin 1 and pin 2, and my capacitor goes between pin 1 and ground. And remember, it's a polarized capacitor, so get that in the right way around. The output is going to come to my LED that goes through a 330 ohm resistor to ground. That output is also going to feed my JK flip-flop. So looking at my schematic, you can see I've filled in all the pin numbers. VCC is on pin 16 and ground is on pin 8. You'll notice the pin numbers for U1A are the same as the pin numbers for U2A, and U1B has the same pin numbers as U2B. Pin 4, pin 3, pin 2, and pin 15 all go to +5. And over here, pin 10, 11, 12, and 14 go to +5. Remember, when J and K are both 1, whenever we get a clock signal in, our flip-flop toggles. So as our clock signal comes in, the first flip-flop will toggle. When that toggles the second time, our second flip-flop will toggle. And so on down. That's why it's called a ripple counter. Pin 5 goes to pin 13 and to an output LED. Pin 9 goes to pin 1 and to an output LED. Pin 5 goes to pin 13 and an output LED. And pin 9 goes to our last output LED. Looking at our LEDs, you can see that the little bar is at this end. So this would be the long leg. This would be the short leg. And we go through a 330 ohm current limiting resistor to ground. So the ICs provide the logic 1 to turn on the LEDs. This is LED A, so it should be our least significant bit, and it comes from our first flip-flop. LED D is our most significant bit, and it comes from our last flip-flop. So you can see here that the output from my clock becomes the input for my first flip-flop. You'll notice at the end of my trainer, I have power coming into an LED going through a resistor to ground. That way I can tell if power is getting to my trainer, even if my circuit's not working. Also note, I've hooked up the power bus, top and bottom, and I've hooked up the ground bus, top and bottom. I want you to notice all these little red wires are +5. Remember, one pin of the IC is power, the other corner is ground, all the others are our JKs and our presets and clears. So if you neatly connect your powers and your grounds, the connecting signals are a lot easier to see. So you can see on pin 1 is my input from my clock. Pin 5 of the first flip-flop goes to pin 13 of the second flip-flop. Pin 9 of the second flip-flop goes to pin 1 of the third flip-flop, and then pin 5 of the third flip-flop goes to pin 13 of the fourth flip-flop. The output I'm taking from pin 13, pin 9, pin 13, and finally pin 9. So when you power up your circuit, you don't know what count it's going to start at. So you're going to have to wait for it to get back to 0, there. And then it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and back to 0. So filling in your truth table for the binary count, start at all zeros, then it went to 0001, and then 0010, all the way up to 1111. Then to fill in your hex and decimal count, on this side we're going to have the hex numbers, so 0 up to 9, and then A, B, C, D, E, and F. And for the decimal count, we go 0 to 9, and then it becomes 10, 11, 12, 13, 14, and 15. You have to know how to convert from one numbering system to the other. So once you've wired up part A of your circuit and verified that it is working, demonstrate it to your instructor so that they can initialize it to indicate that it is complete. Now please note that there is a note here in bold, leave this circuit on your trainer because you're going to need it for part B of the lab. So for lab schematic part B, ripple asynchronous down counter. The circuit is identical. The only thing we're going to change is the output is going to come off of our Q0 and go to our clock. So instead of going from pin 5 to pin 13, we're now going to go from pin 6 to pin 13, and pin 7 to 1, and pin 6 to 13, and we're still going to take our outputs off of our Qs, so don't move them. So looking at my circuit, you can see I come off of pin 5 for my output wire to the first LED. Pin 6 now comes around and goes to pin 13, and that's the clock input on the second JK flip-flop. Pin 7 now goes to pin 1, which is the clock on my third JK flip-flop. But the output still comes from pin 9. Then on my second JK flip-flop, you can see the output from the third flip-flop is still on pin 5. But now pin 6 goes to pin 13, which is the clock input on the fourth JK flip-flop. And pin 9, which is the Q, still goes to the last output LED. So when I start my counter, I don't know where it's going to start. That's 0, that's F, that's E, that's D, that's C, that's B, that's A, that's 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, back to F. So on our truth table, we're going to fill in 1, 1, 1, 1 as our starting position and work all our way down to 0, 0, 0, 0 before it repeats. Then filling in our hex decimal count, you can see we started F, E, D, C, B, A, 9 down to 0. And our decimal count 15, 14, 13, 12, 11, 10, 9 down to 0. Once you've wired up your circuit for part B of the lab and verified that it is working, demonstrate it to your instructor so that they can initial it to indicate that it is complete. So part A and part B were ripple counters. Now we're going to build a parallel or synchronous counter, and you'll notice the clock signal comes in and the clock goes to every single one of the flip-flops. Some of the pins still go to power, so remember to leave those hooked up. And then the output Q goes to the J and K of the next flip-flop. Then the Q and the next Q go through an AND gate to go to the J and K of the next flip-flop. And the output of the first AND gate with the Q of the third flip-flop generates the 1 and 0 for the JK on the fourth flip-flop. For those of you who are having trouble understanding parallel counters, section 10-3 in your textbook gives you a complete description of parallel counters and how they work. So part C of the lab is a fairly complex circuit. Most of the JK flip-flops can be left from the previous circuit, but now we're going to be using these AND gates, and all the clocks get connected together, so there's just one clock going throughout the entire circuit. Now this makes the circuit run a lot faster than the ripple counter. Unfortunately, you need to decode each stage as it goes through. Because this was a fairly complicated circuit, you can see I've highlighted all my connections as I've put them onto the breadboard. So this is my completed circuit. All the blue lines here are the actual clock signal going into my JK flip-flops. A lot of times students tell me they haven't left enough space to wire up an AND gate or another gate into a circuit. Perfectly okay to put it on this side of your output LEDs if you don't want to move them. Powering up the circuit, you never know where it's going to start. So you usually wait for it to get to 0. So that's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and back to 0. So filling in my truth table, you can see I'm putting in the binary count, all zeros, then 0001, 0010, all the way up to 1111. The hexadecimal count was 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, and reset back to 0. The decimal count was 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then reset back to 0. Once you've wired up your circuit for part C of the lab and verified that it is working, demonstrate it to your instructor so that they can initial it to indicate that it is complete. So the lab schematic for part D consists of one IC. It's the 74LS192. It's a BCD up-down counter, and it happens to be programmable. So this is the input number that we're going to start with, and you can see that A is going to be 1, B, C, and D are going to be 0. So it's going to start at 1. The carry out, or once it reaches its maximum count value, now this is a BCD counter, so once it reaches 9, we're going to do a load. So it's going to count up, so we got our clock going into up. If our clock was going into down, it would be a down counter. So it's going to count up, and it's going to start at 1, 2, 3, 4, 5, 6, 7, 8, and then it's going to hit 9. So our carry out is going to be active low. Our load is active low. So when it reaches 9, it should go back to 1. So this counter should count from 1 to 9. So this is my completed circuit. You can see I have the 74192 in my trainer. Power and ground, of course. Only one clock signal coming in, and the clock signal is going to pin 5, meaning this is going to count up. You can see right here is pin 12 and 11 connected together. So when it reaches its terminal count, it's going to do a load. What's it going to load? Pin 15 goes to power, so that's a 1. And then pin 1 goes to ground. Pin 9 and 10 go to ground. So it's going to load in 1, 0, 0, 0. These are my outputs going to my LEDs. And you can see right now I'm at 6, 7, 8, 9, back to 1. Notice the 9 back to 1 is not a full count. So, filling in my truth table, you can see it starts at 0, 0, 0, 1, and then goes to 2, 3, 4, 5, 6, 7, 8, 9, and back to 1. You notice it only asks for a decimal count because it only counts up to 9, so a decimal count or a hex count will have the same numbers, 1 through 9. Once you've wired up your circuit for part D of the lab and verified that it is working, demonstrate it to your instructor so that they can initial it to indicate that it is complete. So under lab schematic part E, this looks like a fairly large circuit, but it's not. It consists of U1A and U1B, which is the CMOS IC counter. So there's two counters in one IC. We're going to be using two AND gates, and of course they're in one IC. All by itself, if you put in a clock signal and run the clear line to ground, this will count 0 all the way up to F. So it's just a binary counter. Counts 0 to 15 and starts over again. So what we want to do is we want to count from 0 to 9. So 9 is 1. That's the 8th column. So 9 is 1, 0, 0, 1. Now 10 is 1, 0, 1, 0. So when it gets to 10, it's going to activate our AND gate that's going to come back and clear our first counter. So our first counter, with the addition of the AND gate, should count from 0 to 9, and as soon as it hits 10, it's going to reset. Also notice that that reset line comes all the way around and goes into the clock of the second counter. So every time this gets to 10, this clock's going to count 1. So we want this particular counter to count from 0 to 5. We're trying to get a 60-second counter here. So if our clock signal is 1 hertz, this will count 0 through 9, and then this one we want to count 0 through 5. So 5 is 0, 1, 0, 1. The next count is 6, which is 0, 1, 1, 0. So when we get the two ones in the middle, it's going to activate this AND gate, which is going to clear the second counter. The first counter should have already reached 10, so it'll be 0. The second counter will hit 6, it will go to 0, so we'll have 0, 0. So this is my circuit wired up, and you can see the original clock signal comes in on this blue wire and goes to my counter. So this is the 393. That means that this one has to be the 7408, and I'm going to use two AND gates on it. You'll notice the outputs for the most significant digits go straight over to the LEDs. So this is my most significant digits, and that's going to count 0 through 5. So power comes from the IC, goes through the LED, through the current limiting resistor to ground. Now this is my least significant digit. It counts 0 through 9. And you'll notice its outputs on the 393 are on this side of the LEDs. So rather than routing my wires up, around, and over, I decided to route them straight across. So this is the positive side, or the long leg of the LED. The other side is the short leg that goes through the 330 ohms to the ground bus. Remember, you have two ground buses, one at the top, one at the bottom. You don't always have to use the bottom ground bus. And in my case, I decided to use the top ground bus so that my output wires are nice and straight and it looks neat on the breadboard. Also notice I don't have any wires crossing my ICs. A lot of times you guys tell me I've got a bad IC. When we go to replace it, we have this great big bunch of wire going across all your ICs that we have to separate to put in a new IC. So if anything's wrong with my ICs, they're easy to pop out and replace without having to move a whole bunch of wires. This is my circuit working. That's 6, 7, 8, 9, and there's 1, 0. There's 8, there's 9, 2, 0. Eight, 9, 3, 0. Eight, 9, 4, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 5, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 2, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 3, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 4, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 5, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 60. 1, 2, 3, 4. Once you've wired up your circuit for part E of the lab and verified that it is working, demonstrate it to your instructor so that they can initial it to indicate that it is complete. On the last page of the lab, we have 10 questions for you to answer and hand in. If you are looking for answers, open your textbook, and on page 1 of the lab it shows some hints. In this case, it's solve problems 10.1 through 10.41.